Okay, let's look at some more complicated looking logarithmic equations. In this one, you'll notice that I have on the left-hand side two logarithmic expressions, right? We would like to be able to, if possible, combine this as one logarithmic expression. And we're going to use the properties of logarithms. So let's just, again, rehash those properties of logarithms. Okay. And I'll do these in general, so log base A. And if you remember, log base A of a product, say u times v, is what? What do I do when I multiply like bases to different powers? What do I do with their powers or logarithms? I add them. Number two was if I have log base A and I'm taking the logarithm of a quotient, what do we do with the exponents when we're dividing like bases? We subtract them. And number three then, this is the one we've already used, log base A of say u to n to some power. This is n times log base A of u. So these are the properties of logarithms that you need to know and use. In particular here I have log, what's the base? There's the base. There's what? It's got to be log base 10, right? And that's the common logarithm. If we don't have a base, we assume it's always 10. But again, if I just have log, that applies here. And so notice I have log of x plus log of x plus x minus 3. I can condense this by property number 1, right? Going from here to here. In other words, this is the log of x times x minus 3. So condensing it, going from a sum of logs to the log of a single quantity. That's what I want, a log of a single quantity equals 1. Now I can write this in exponential form, right? So log, we said was base 10, right? Log base 10 of this quantity is 1. 1 is what? The exponent on what? The base. 10 to the first power is x times x minus 3. What kind of equation do we have here? It's quadratic. 10 to the first power is 10. Now, I'm going to have to do some work here, distribute this x through, right? And what do we get? We get x squared minus 3x. And so let's write this as x squared minus 3x. If I subtract 10, I'm left with 0 over here, and there's that quadratic equation. This one, again, is very easy to factor. I've seen this in the previous example as well, right? The product is negative 10, the sum is negative 3, so this is negative 5 and positive 2. So notice positive 2x, negative 5x for the outer and inner, give me the negative 3x term. So make sure you FOIL this out to check. Make sure you're checking the factoring or solving of this equation as well. So x minus 5, since I have it equal to 0, is 0, or x plus 2 is 0. In this case, x is 5. In this case, x is negative 2. Now, it's going to be real important to check. You have to check here because one of these solutions is extraneous. What do I mean by that? Certainly 5 and negative 2 satisfy this equation. But when I go back to what I started with, notice here that this tells me, since I have the log of x, remember x has to be greater than 0. The domain of the log function is only positive numbers. And this here means what? That x minus 3 has to be greater than 0. Because that's what I'm plugging into this log function. Well, if x minus 3 is greater than 0, x has to be what? Greater than 3 if I add 3 to both sides. Right? This is very important. Right? Right? And this tells me that this solution that I came up with, right, this is what we call an extraneous solution. Extraneous solution. All it means, if I try and plug negative 2 back in here, I've got problems, right? Because it doesn't work in either one of these, right? It doesn't work in either one of these expressions. Okay? The log of negative 2, log of what, negative 5, those are not defined. So again, negative 2 satisfies this equation. If I plug in x as negative 2, it satisfies this one, but not the original one. So by extraneous, we sometimes get those type of solutions. Now 5 is fine, okay? And that is the solution. Of course, I don't need an approximation, do I? Right? The exact solution is just an integer. So there's the solution. Can we check and make sure? Yeah, we can. I mean, I can come here, and I do have a log button. I can do log of x, which is just 5 now, plus log of what? 5 minus 3, which would be 2. That should equal 1, and it does. And we know that does because, again, I can use this property right here. Log of 5 plus log of 2 is log of 5 times 2, which is log of 10. What is log of 10? Log of 10 is 1 because 10 to the first power is 1. Okay. Well, let's take a look at another example. Now I have 2 logarithms again on this side, right, and 1 again. But this time, what do I notice? I'm subtracting logarithms. Here I was adding logarithms. What do I do when I'm subtracting logarithms? I can combine them as one by what? Dividing, right? The u and the v in this case. So here's the u, x plus 2. Here's the v, x minus 1. So this right here is going to combine to what? Log base 4 x plus 2 divided by x minus 1. Right? Now I've got the logarithm isolated on one side, log base 4 of something equals 1. I write this in exponential form. So the logarithm is what? The exponent. What's the logarithm? It's 1. What's the base in this case? 4. So 4 to the first power is x plus 2 divided by x minus 1. Of course, 4 to the first power is just 4. Now, how do I solve this equation? I multiply both sides by x minus 1. And then I have just a linear equation. I solve for x. Distribute this forward. Subtract x from both sides. 4x minus x is 3x. X minus x is 0. And add 4 to both sides. I get 3x. 2 plus 4 is 6. Divide both sides by 2. X is 3. Oh, divide both sides by 2. That's real good. Divide both sides by 3. X is 2. Of course, I'm going to check, right? So if I made that simple mistake, I would know it doesn't work, right? I can go back and check. Now, one thing about this is I don't have a log base 4 button, so I'm just going to plug back into the original equation. So when I want to check this, there's my solution. Check what is log base 4 of x is 2, so 2 plus 2 divided by 2 minus 1. Well, 2 plus 2 is 4, 2 minus 1 is 1, so this all is equal to what? So the thing inside here is equal to what? Log base 4 of 4 divided by 1, 4. What's log base 4 of 4? What's the power of 4 needed to get 4? 4 to what power is 4? It's 1. Right? So indeed, it does indeed check. If I had done 3 here, right, like I had done, I would, you know, so 3 plus 2, I'd have 5 divided by 2, and I would know something's wrong. It wouldn't check. So again, make sure you check, because you can make simple mistakes like I do. Dumb little things like that will cost. Okay. Again, properties of logarithms. Now, let's take a look at this one here. Now there's two ways we can proceed here. Notice we have logarithms on this side, but also on this side. I can combine these two as one logarithm. If you remember, the sum of logs becomes the log of the product. So this becomes the natural log of x minus 4 times x plus 1. Now, I could subtract this logarithm, log base e of x minus 8 from both sides, and then use properties of logarithms to write this as, log of a quotient. But notice here, real important here, if the natural log of a equals the natural log of b, the logarithm is a one-to-one function, then I automatically know that a must be equal to b. Okay? And for general functions, that's not true, but the logarithm is increasing or always decreasing on its domain, and so if the outputs are the same, the inputs are the same. Okay, and so I can use that idea here to say that x minus 4 times x plus 1, the input over here must be the same as the input here. Okay. Now we'll solve this, and so how would I solve this? This turns out to be quadratic. I've got to FOIL this out. I get x squared. The outer is plus x. The inner is negative 4x, and the last negative 4 times 1 is negative 4. Combine x minus 4x, negative 3x, and then I'm going to set it equal to 0. Subtract x from both sides and add 8. Negative 3x minus x, negative 4x, add 8, negative 4 plus 8 is positive 4. And this thing then factors as x minus 2 quantity squared. It's a perfect square. I recognize the pattern here. I've got a perfect square here, a perfect square here, and this is 2 times 2x. So what's that mean? X equals 2. Right? So there's my solution, right? I just go on my happy way. I'm going to just type that in and move on to the next problem. Not so fast. Go back to the original and notice, for instance, right here, right? X minus 8 must be what? Greater than what? 0, because it's inputted into the log function. If x minus 8 is greater than 0 rather, then x must be greater than 8. X must be greater than 8. Well, if x is greater than 8, what do we know? This is not a solution. So do we mess up? Do we miss one? Where's the solution? What is it? We've got the only possibility here was 2, and that doesn't work. And so what do we say? There is no solution. There's no value of x that will satisfy this equation. Okay. Now you can write no solution. Now other notations could be sometimes the empty set, or there's a symbol with a circle with a line through it. These are what we refer to as the empty set. So check directions. Which way are you going to define that? But no solution. There's no value of x that will satisfy the original equation, and that can happen. That can certainly happen. Now, I wanted to say that you could have also done this problem another way once we came to here. Or I said you could have subtracted this from both sides, so natural log of x minus 4 times x plus 1 minus the natural log of x minus 8 equals 0. And then you can combine this, right? Log of something minus log of something. I can combine that as log of what? This stuff over this stuff. So it's the natural log of all this stuff. And then I can use this is a logarithmic equation, right? Natural log, right? Log base e of all this stuff is 0. So the logarithm is what? The exponent. The exponent is 0 on what? The base, e. E to the 0 is equal to x minus 4, x plus 1, all over x minus 8. What is e to the 0 equal to? It's 1. And if I solve this equation, then what do? Multiply both sides by x minus 8. When I do that, what do I get? neglected here, right? X minus a equals x minus 4 times x plus 1. So again, you could do it either way, but I like this idea here. If you remember that the logarithm is a one-to-one function, if log of a equals log of b, then a has to equal b. Okay. But either way, we come up with no solution for this. Okay, so we will do one more video of a little application next.